Hello. So we've shown that the solution to the Ramsey-Cass-Koopmans model is characterized by two differential equations. One, a C dot equation that tells us how consumption evolves over time, and the other a K dot equation that tells us how capital moves over time. However, a path that satisfies these two equations is not necessarily an equilibrium, and that's what we're going to look at today. First, it's very easy to see that there is going to be a steady state equilibrium or balanced growth equilibrium here where C dot and K dot are zero. How do we see that? Well, take your C dot equation and set C dot equals to zero. If you examine it carefully, you'll see that there is one and only one value of capital for which that is going to hold. Take that value of capital, plug it into the K dot equation, set K dot equals to zero, and you'll see that there's only one consumption level for which that will hold, and so that value of capital and the value of consumption, small k and small c, are the steady state. However, the steady state is not the only equilibrium. What we're going to do is we're going to study graphically how it is that different paths that satisfy these two differential equations will evolve in the space of consumption and capital. We're going to draw two axes with consumption on the vertical axis, capital on the horizontal axis, and see what the paths look like in that space. What we'll find is that there is a unique equilibrium for any given level of capital that you start with. A unique equilibrium meaning a unique level of consumption from which you will proceed directly, gradually, to the steady state. Let's take a look. Now that we've derived the key differential equations that characterize the Ramsey-Cass-Koopmans growth model, what can we learn from them? To do that, let's just set them apart first of all. And notice that we can do the following to try and understand how these equations are going to work. Suppose that we set C dot equals to zero. This is going to hold for one and only one value of capital. Therefore, we could imagine drawing a figure where consumption is on one axis, capital is on the other axis, and we can represent that line, the line where C dot is equal to zero, in this space. Of course, it would be a vertical line because there's only one value of capital for which this holds. This is concave and increasing. This is linear and decreasing. And so this function of capital is going to go up and then down. Therefore, if we rearrange this equation, the C that makes this equation hold for any given K is going to also go up and then down. And so what we're going to do now is look at precisely that graph and see what that tells us about this economy. So here is that space. On the vertical axis, we have consumption. On the horizontal axis, we have capital. And as discussed, there is one and only one value of capital for which C dot equals 0. And so let's represent it here. Now there is also a locus, a line, that represents all the points where K dot equals 0. To determine those, let's go back to our equations. Again, remember that this is our state equation. The locus we're interested in, the line we're interested in, is the one where K dot equals 0, which, as we showed earlier, is a line described by this relationship. And if you look at this is U-shaped because this is a concave function, this is a linear function, a negative one, and so this will go up and down. So returning to this figure, this line is going to look like this. I've tried to make it concave, and also I've made it go through 0, which is based on the assumption that the production function produces 0 output if there is 0 capital. There is a reason why the peak of this locus is over here, higher than where these two lines cross, but don't worry about that right now. The next thing we need to do is to go back to our equations. Now suppose capital is higher than the value where this is 0. F is a concave function. Therefore, f prime is decreasing in k. So if I raise k, that means this C dot has to go down. And that means that if I am at any k above this k for which C dot equals 0, it must be that C is decreasing, whether it's up here or down here. By the same argument, if we're over on this side, it means that if capital is below the level for which C dot equals 0, then C must be increasing, regardless of which of these 4 regions we are in. Now, going back to the equations, this equation assumes that K dot is 0. So if C is higher than that, it means K dot must be negative. And if C is lower than that, then K dot must be positive. So that tells us about how to think about how K is going to move. If C is higher than this equation, then as discussed, K must decrease. If C is lower, then K will increase. And that tells us quite a lot about the dynamics of this environment. What can we do next? what we can do next is look at possible trajectories within this space. By the way, what we're looking at here is what's called a phase diagram. The first thing to observe is that there is a steady state. At this point, C dot equals 0 and K dot equals 0. And that means that we have a stable equilibrium. As long as when time started, the value of small k happens to equal this one. If so, then this model is on a steady state where C grows at a constant rate, K grows at a constant rate, and everything is in balance. However, what if we started off with a different level of capital? Well, let's study that. Let's pick a starting point. Suppose we start from some point in here with a particular K0, and let's just pick a particular C. Following the differential equations that we have, we're going to go up and to the right. And there are two possibilities. One is that we cross this line. And then, of course, once we're in this area, we will go up and to the left. Another possibility is that we go up and to the right, and then we cross this line, and then we're going down and to the right. That might make you think that maybe there is one, and of course only one, specific line that does not diverge in either direction, but actually heads towards the steady state. Now let's pick a dot over here. It goes down and to the left. So let's go down left. If we ever hit this line, we're going to go down to the right. Another dot over here, we're going down and to the left. And if we ever cross this line, we're going to go up and to the left. Again, that suggests there may be a unique line that actually takes us straight here. Now, mathematically, we can prove that that is exactly the case. There is one and only one line that, given your starting point in capital, there will be one choice of consumption that takes you to the steady state. And that's great. It means that we have a unique equilibrium. Any other choice of consumption that satisfies those differential equations, by the way, is going to diverge. It's going to lead to consumption being 0, which of course makes no sense, or capital being 0, which of course makes no sense. And thus, we've shown that not only does this model have a unique steady state, which is where the two C dot equals 0 and K dot equals 0 lines cross, but we will also have a unique equilibrium in general. Give me your K0. I can find you the unique equilibrium value of consumption. And moreover, that path, given that choice of consumption, will converge to this steady state. So what we've seen is that not all paths that necessarily satisfy these two equations are equilibria, but by doing a little extra work, in particular by using a phase diagram, we can figure out what equilibria look like in general in this environment.